Hey everyone, welcome back to the channel. Today I'm super excited to share something really fascinating with you, a deep dive into the second place solution from the WSDM Cup Multilingual Chatbot Arena competition. Have you ever wondered how AI models can be trained to judge which chatbot response is better? That's exactly what this competition was about, and the approaches used are absolutely brilliant. I've been studying this winning solution from Kaggle user Zhudong 1949, and I'm going to walk you through exactly how they achieved such impressive results. Whether you're a machine learning practitioner, a competition enthusiast, or just curious about how AI preference prediction works, I think you'll find some really valuable insights here. Let's dive in. So as you can see, we're looking at the second place solution for the WSDM Cup Multilingual Chatbot Arena. This was a fascinating competition where participants had to predict which chatbot response users would prefer in head-to-head battles. The winner was a Kaggle user named Zhudong 1949, and I've created this analysis to help us all learn from their approach. Let's start by understanding what this competition was actually about. The challenge was to predict which response users would prefer when presented with two different chatbot answers to the same prompt. The dataset provided included training data with prompts, pairs of responses from two different models, and labels indicating which response was preferred. The test data had similar prompts and responses, but without the winner labels, that's what competitors had to predict. What made this competition particularly challenging was its multilingual nature. The prompts were in various languages, so models needed to handle this diversity effectively. The goal was to identify those subtle quality differences between responses that make one answer better than another in the eyes of human evaluators. The submission format was pretty straightforward, just predicting whether Model A or Model B was the winner for each test case. Here's a real example from the competition to give you a better sense of what we're dealing with. Look at this prompt, "Please be boring." Simple enough, right? But the way different models interpreted this request is fascinating. Response A actually took a narrative approach, describing a deliberately mundane day, waking up at 6:30, drinking plain black coffee, taking the same route to work, etc. It's literally being boring by describing boring things. Response B, on the other hand, took a more functional approach, basically saying, "I'll be straightforward and unadorned," and then explaining what that means in a structured way. Human evaluators actually preferred Response A, the one that was deliberately boring in its content rather than just being functional. This highlights one of the key challenges for AI models in this competition: understanding the nuance of human preferences and how they relate to the actual intent behind prompts. Moving on to the technical approach, the solution built on a code framework from another user, Task 0, from a previous competition. This framework was already optimized for efficient training with limited GPU resources, in this case, 4 A100 GPUs. For base models, they started with two models, Gemma 29B and Armo RM Llama 38B. Interestingly, both were initialized from Task 0 pre-trained models, showing how competitors often build upon previous work. One key modification was changing the classification head from 3 outputs to 2, which makes sense given that they only needed to predict which of two responses was better. The tech stack was pretty standard for modern NLP work. PyTorch with FSDP, Flash Attention 2, Triton, and Xformers, all tools designed to make training large language models more efficient. Now, data processing might sound boring, but it's actually super critical to performance. One of the clever innovations here was using something called MID Vita Processor PIB for handling long text. Instead of just truncating text from the beginning or end when it's too long, they used proportional middle truncation. This preserves both the beginning and ending contexts while removing some content from the middle. It's like keeping the introduction and conclusion of an essay, but trimming some examples from the middle. This approach is much better than simple head or tail truncation because those critical first and last impressions that responses make are often what humans remember most when judging quality. Their custom sequence length handling ensured they could effectively process prompts and responses of various lengths. For their first submission, they used a 4-step approach that's actually quite elegant. First, they fine-tuned their base models on the competition data. Then, they used these models to create pseudo-label data, essentially using their strong models to generate predictions for additional data that didn't have human labels. Next, they fine-tuned again using both the original competition data and these pseudo-labels. And finally, they applied something called test time augmentation, which is a really clever technique where they leveraged predictions from multiple models looking at the data in different ways. The key strategies here were pseudo-labeling to overcome limited labeled data and test time augmentation to improve prediction robustness. Both are powerful techniques in competitions where the amount of labeled data is limited. Let's look at the specific steps for the first submission in more detail. In Step 1, they fine-tuned several models: LMSys Gemma Pretrain, LMSys Llama Pretrain, and Gemma 227B. They used 80% of the training data plus a 20% validation set for this initial training. For creating pseudo-labels in Step 2, they used datasets from another competitor, at NBroad, one with 8.5K samples and another with 13K samples. They averaged predictions from their 3 models to create soft labels, resulting in a dataset they called HF21K. In Step 3, they fine-tuned their base models with this HF21K dataset combined with 80% of the WSDM competition data, creating models they called Gemma Pseudo and Llama Pseudo. Finally, for test time augmentation, they had Gemma Pseudo predict on the data in the original order, PAB, while Llama Pseudo predicted on the data with responses swapped, PBA. The results were weighted at a 3:3:1 ratio, giving more emphasis to the Gemma model predictions. This approach gave them a leaderboard score of 0.709 and a private score of 0.708, already very competitive. For their second submission, they dramatically expanded their data approach. They started with the LMSys Chat1M dataset, which after deduplication gave them about 424,000 English samples and 103,000 non-English samples. From this, they created several sampled datasets with different language balances. They made VLLM v1 with 10,000 samples, 7,000 non-English and 3,000 English. Then VLLM v2 with 27,000 samples, 21,000 non-English and 6,000 English. And finally, VLLM v3 with 38,000 samples, 36,000 non-English and 2,000 English. Notice how they're progressively increasing the proportion of non-English data to improve multilingual performance. This is really smart given the multilingual nature of the competition. For response generation, they used VLLM inference with a whole bunch of models, from QN2, 572B down to smaller models like Llama 3.21B. This diverse set of models helped generate a variety of responses that would later be pseudo-labeled. For the second submission's training strategy, they first combined all their pseudo-labeled data, the HF21K from before plus the VLLM 74K for a total of 95,000 samples. They then retrained their base models to avoid pseudo-label noise, creating new versions called Gemma Pseudo v2 and Llama Pseudo v2. For final training, they split the WSDM competition data into an English subset with 90% of the English data and a multilingual subset with the remaining 10% of English data plus all other languages. Then they used a clever 2-phase training approach. In the first epoch, they trained on the English subset. Then in the second epoch, they trained on the multilingual subset. This created their final models, Gemma Final and Llama Final. This 2-phase approach is really interesting. They're first building strong English language capabilities, then fine-tuning specifically for multilingual performance. It's like learning the basics of language comprehension in one language before expanding to others. For their inference strategy in submission 2, they again used test time augmentation, but with a more selective approach. The Gemma final model predicted all data in the original order, PAB. But the Llama final only predicted data where the confidence difference between the two responses was small, using the swapped PBA order. They weighted the ensemble at a 2:5:1 ratio. This selective approach is clever. They are only using the second model in cases where the first model isn't very confident, which is exactly where a different perspective might help. The results showed the same leaderboard score of 0.709, but an improved private score of 0.716, which secured their second-place finish. The key improvements in this submission were more diverse pseudo-labeled data, better language balance with increased non-English data, the two-phase training strategy, and their more selective ensemble approach. It's always valuable to know what didn't work as well as what did. They tried several approaches that weren't successful. They experimented with QN2, 572B distillation, but were limited by time and GPU resources, managing only one fine-tuning cycle without pre-training. They also tried using Skywork reward models for pseudo-labeling and as base models, and attempted to use external datasets like Skywork Reward Preference 80K for training techniques. They tried binary target loss and multi-loss weighting, but these didn't provide improvements. The key lesson here is that simpler approaches with carefully curated data and strategic training often outperform more complex techniques. Pseudo-labeling quality and language balance were more important factors than sophisticated model architectures or loss functions. This is something I've seen time and again in competitions. Sometimes the most elegant and straightforward approaches win out over complicated methods. So what can we learn from this solution? There are several key takeaways. They found that pseudo-labeling really helps when you have limited labeled data. Test time augmentation improves how robust your predictions are. Focusing on multilingual capabilities in the final training stages was crucial. Their strategic data sampling with language balance made a big difference. And that two-phase training approach starting with English and then moving to multilingual was super effective. On the technical side, they used efficient training with FSDP and flash attention too, model ensembling with weighted predictions, data processing with middle truncation, base models from previous competition winners, and custom confidence thresholds for selective ensemble predictions. Perhaps the most impactful factor was the quality and diversity of their pseudo-labeled data, especially for multilingual capabilities. This really highlights how data quality and representation can be more important than model complexity in many cases. And there you have it, the second-place solution with a leaderboard score of 0.709 and a private score of 0.716. Their final approach used Gemma 29B and Armo RM Llama 38BV01 as base models, 95,000 combined pseudo-labeled samples, a two-phase English to multilingual training strategy, and test time augmentation with selective thresholds. For future improvements, they could consider integrating larger and more diverse models, more sophisticated language-specific training, better cross-lingual transfer techniques, and deeper exploration of model confidence calibration. If you're interested in diving deeper into this solution, check out Zhudong 1949 GitHub repository. I'll leave the link in the description below. I hope you found this analysis helpful. If you did, please hit that like button and consider subscribing for more content like this. I regularly cover interesting AI competitions, machine learning techniques, and practical applications. What do you think about this approach? Would you have tried something different? Let me know in the comments below. And if there are other competition solutions or AI topics you'd like me to cover, I'd love to hear your suggestions. Thanks so much for watching, and I'll see you in the next video.